Now, there's a trivial way in which saying that there couldn't be a physics without observers would be like that. I mean, there are observers in the world, so it'd better be the case that our physics can allow for the existence of observers, and it might be that there are some aspects of the study of observers, like the study of zebras, that require concepts coming from physics. But I take the conference to be thinking of something more exalted than that, if you like, that somehow there's a question about whether our physics requires the notion of observers in a deeper way. And I just want to quickly give, I think that there are 3 places where that seems to be coming up. One of those is there something about the nature of consciousness which means that understanding humans is not, human consciousness is not a problem for neuroscientists and psychologists and AI researchers, but somehow is relevantly a project in fundamental physics? Secondly, do we have a formulation of quantum mechanics that excludes observers from it, or does somehow the very nature of how we understand quantum mechanics require observers? Thirdly, does our understanding of modern cosmology and the epistemological questions in cosmology require us to think seriously about observers? And I'll just state without defending, I think I'm 1 for 3 on that framework. I'm perfectly happy to leave consciousness to the neuroscientists and the psychologists and the AI researchers. I think I agree with Jim Hartle that what we've got in the last 50 years of work on the foundations of quantum mechanics, starting with Everett's work, going through the development of theory of decoherence, has given us a way of doing quantum mechanics in which observers don't play any foundational role. But it does seem that we have some big problems at the moment in thinking about the epistemology of cosmology, the sort of issues that Anthony raised at the beginning of the conference, that really do seem to be, at the moment at least, confronting us with the need to bring observer concepts into physics. So insofar as we can't do a physics without observers, I think my take on it is we can't at the moment at least because we don't know how to solve those epistemological problems and tell a third-party story in the way that we're used to in the rest of physics and in the rest of science.
Thank you, David. Alan, would you like to say a few words?
Okay, I'm Alan Guth from MIT. My main work, as you probably know, is in cosmology, so I'm mainly interested in the question of the role that observers might play in cosmology. I agree very strongly with what Jim Hartle said about observers, namely that, as far as I can tell, there's no reason to think that observers have anything to do with the fundamental formulation of the laws of physics. But that nonetheless, when we test our theories, we are testing observations made by us, and that's a conditional probability issue. We do have to understand what our theories predict that observers should observe, thinking of observers simply as physical objects in the universe that our fundamental theories describe. I disagree very strongly with the ending of what Jim spoke about concerning observers. An important issue about observers in cosmology is this Boltzmann brain issue. That is, for those of you who may not be familiar with it, if inflation leads to eternal inflation, which most of our models of inflation do, meaning that once inflation starts, it never stops, but new pocket universes keep budding off ad infinitum, that leads to a problem about defining probabilities, because anything that's allowed by the laws of physics will ultimately happen an infinite number of times. So if you want to imagine that some kind of an event, like the birth of a 4-headed cow, is less frequent than the birth of a 1-headed cow, you have to face the basic fact that each of those are going to happen an infinite number of times. So it's hard to know what you mean when you say that one is much more probable than another, or much more common than another. So many of us in cosmology have been wrestling with this problem for 15 years or more. We call it the measure problem in cosmology. And the basic status, as I would summarize it, is that we have proposals for measures, that is, proposals for methods of regularizing the infinite spacetime of an eternally inflating universe. And then we define probabilities by the ratios of numbers of occurrences in that regularized spacetime, and then take the limit as the regulator goes away. But it turns out that things are very sensitive to the kind of regulator you introduce, and we don't yet know what principle should determine what the correct cutoff should be. So one of the important issues is this Boltzmann brain issue. Some of these measures, some of these proposals for how to define probabilities predict that the universe should be dominated by Boltzmann brains, brains that could be literally identical to my own or your own, but which was created not by evolution from a Big Bang, but rather just as a thermal fluctuation or a quantum fluctuation that happens in an otherwise essentially empty region of this space-time. Many of us, including me, believe that any proposal which predicts that beings who think that they're Alan Guth and have all of my memories are mostly Boltzmann brains, which would be the case for many of these measures, I would say that such theory should be rejected, because I have no idea of no way of knowing which one of those people I am. So I have to assume I'm equally likely to be any, I think. That would mean that I would be making a prediction that if I look outside the window, if I was a Boltzmann brain, I would expect to see chaos. When I tried the experiment last, I didn't. So I would conclude that such theory should be rejected. Jim is proposing that it's okay to accept such theories. We just add the postulate that I'm atypical. I guess I'm giving you everything I wanted to say. Maybe I shouldn't have said so much. But let me still finish this thought, because otherwise I'm leaving it in midair. I think if you're willing to say that, then all experimental physics goes down the drain. Suppose I'm just talking about dice and asking whether a die is fair or not. If I flip it 100 times in a row, I don't mean a die, let me use a head, a coin. If I flip a coin 100 times in a row and it comes up all heads, if it's a fair coin, the probability of that is 10 to the minus 31. I would reject the possibility that that coin was fair. I wouldn't say maybe I'm just atypical, because atypical observers will see that happen sometimes. So it's my feeling that if you allow yourself to say that you're atypical, you're really throwing away probability theory completely. All probability theory, as far as I can tell, is based on the assumption that we're typical, and all physics really is based on probability theory. So I'll stop there. I spoke too long.
Thank you, Alan. And Adrian.
Is that right? Yeah, that seems to be about right. Hi, I'm Adrian Kent from Cambridge and Perimeter, and I'm really happy to be following two such clear and lucid introductions. I'd written down exactly the same list of 3 places where the question seems to be coming up, as David had. Observers in cosmology. I agree, there's deep problems there. I think we've already heard a lot about that, so I won't add more right now. The second place is the role of the observers in quantum theory and in understanding quantum theory. And it used to be really very common to worry that we needed to know what an observer was before we could really say what quantum theory was. Maybe it's still a worry for some people, for radical subjectivists. But for most of the rest of us who think quantum theory describes an observer-independent physics, well, David mentioned Everett as one line of thought, and it is certainly out there. But there are so many interesting, well-developed, promising options, including many one-world options rather than many-world options, that strongly suggest, or I think should almost persuade us at this point, that we should be able to characterize the space of quantum events or quantum processes by simple mathematical rules that have nothing to do with observers. Okay, so where does one go from that? Well, there is this third question that David's already alluded to, and another David's already given us a very intriguing talk on. The worry about the consciousness of observers. So David Chalmers, William James, and many others have argued, and they have not persuaded everybody, but to my mind they argue very persuasively that there is an unsolved fundamental problem connecting consciousness with the rest of physics. So I realize this divides the community. You may completely disagree. And whether you agree or not, I think we all agree it doesn't, even if there is a problem there, it doesn't necessarily have anything to do with the problems of quantum theory. On the other hand, as David suggested, if you think there is a problem and there are still bits of quantum theory we don't understand, there could be a connection. They could be connected. So I don't want to take that line of thought very far here. I just want to comment that if you do follow that line of thought, it seems to me you're going to need some story that we don't really have at all about consciousness and evolution. I mean, for instance, if you think that consciousness really is doing something important in collapsing wave functions, you'd better have some reason why it's evolutionarily advantageous to develop a wave function collapsing facility. And you could try and run a story like that, and I actually think a few people should be trying to run a story like that. And my maybe most FQXi-friendly preprint I put on the archive recently. Well, on the one hand, it does try to write a story like that, but on the other hand, its existence theorem, to my mind, is to just how hard it is to really get a story off the ground. It seems like a very big roadblock to take this line of thought any further. And I'll stop there. Thank you.
Thank you, Adrian. So before we get to the part where I try and get you to fight each other, we first have the speed round, where I ask you some quick fire questions. And the first one is I'm going to ask each of you for a 1 or 2 sentence max definition of what an observer is. I actually think that this panel has done a better job than previous sessions, if I may say, of actually giving definitions of what it is you're trying to talk about. David, in particular, gave a definition, but can I ask you to each, one after the other, give what you think is a definition of an observer and what a sort of essential characteristic of an observer is, if you want to say it in those terms. Starting with you, Alan.
Okay. Well, I guess I actually will beg off slightly on the question. I don't know that I need to define the word observer in general, but in the context that I'm interested in, which is basically talking about how to go from what Jim Hartle called third person to first person, we're talking about observers like me. And one of the nice features, really, one of the few nice features, really, as far as finding probabilities of this multiverse, is that everything that is physically allowed will happen an infinite number of times. So I'm allowed to restrict my observers, as far as I can tell, to be beings who literally know nothing different from what I know, who are totally indistinguishable from me as far as their internally measurable characteristics. I don't care what they look like on the outside. And there's an infinite number of those, so that's certainly a large enough ensemble to define probabilities and conditional probabilities, which is what the relevant question is. So I think there's no need to go beyond that. As far as I'm concerned, observers are beings who think they're me.
Thank you, Alan. I'll remind the rest of the panelists that I asked you for 2 sentences, and you're not allowed to use quite as many semicolons as Alan did. David.
Yep. Okay, I'll give a philosopher's weasel answer in 2 sentences. I'm skeptical, or at least cautious, that looking for definitions of something like this is the right way to go. Reason 1, because in general, I think, in physics and in science and in philosophy, we very often learn what something does by using it in context, by seeing which structures it fits, by seeing how it fits into other bits of theories, rather than giving sharp definitions. And secondly, because in the case of sort of organized complexity in a Darwinian universe anyway, the kind of mechanisms that deliver this are not the kind of thing that give rise to sharply defined things with sharp boundaries.
Okay, trying to dispense with the semicolons, commas, and other kinds of grammatical curlicues. Sorry?
That was Susanne.
Okay. Positive phrases. So in the context of quantum mechanics, pure states, I have long thought that Everett's thesis is one of the most beautiful papers of the 20th century. As far as other more classical mixed state kinds of domains, that's what I talked about, is one possibility, period. One thing that I'm quite intrigued by is seeing what kinds of connections these might have, because if we could take classical quantifications of what we think an observer means and relate them to the much more pure, clean, distilled notions of Everett quantum mechanics, it might provide some new kinds of insights into these very, very misty borderlands.
So me, all the things I care about are observers. Microbes, animals, humans, every living thing is and has to be an observer. And all these things learn to react to their environment, which is something that non-living things don't do. I've never met a non-living thing that learns. And we don't really have a proper physics-based theory for learning. And I would like to think, or to hope to think, that that's actually something that should be within the realm of physics and not within the realm of some other discipline, that we want to understand and explain learning from the bottom up, from first principles. And so I haven't defined observer. But now I have to define observer. So I kind of agree with Ellen that maybe a general definition just isn't necessary, and you should define it within the context of what you're trying to do. And so within that context of what I'm trying to do, my pathetic attempt to get from physics to learning theory, I've defined it for you today. It was just a simple machine, data in, observation out. But that's obviously not good enough. So I also believe that quantum mechanics is the way to go there.
What about squirrels?
The squirrels, huh? I should never have said that. I couldn't sleep all night because of those squirrels.
Can you define learning?
Can I define learning? No, I don't really think I can define anything, to be honest, because philosophers define things, right? So let me give you a really pathetic example. Think about a cliff, and take a rock up your favorite cliff, and a large rock, a substantial rock, a hard rock that doesn't like fall apart so easily, right? And throw that rock down, and then go back down, pick it up, and do it again. Second experience will be rather similar for you than the first experience, right? Now repeat that experiment with David. The second time you try to throw him off the cliff, it'll be a rather different experience for you.
Even the first time.
Because he learned. This is not going to happen the second time, right?
Okay, I'll try and keep it short. I don't know. It is possible that there is no fundamental notion of observer in fundamental physics. It's possible it's a very useful higher order concept, roughly along the lines of the IGUS that Jim has mentioned. The alternative is, I suppose, it's something to do with consciousness, and we don't understand anything scientific about it. And maybe we can, and maybe we can't, but I don't know.
Surprisingly, on this point, and this point only, I agree with Alan. We have a theory consisting of a Hamiltonian, a wave function of the universe, and a zero-graphic distribution. We want to test that. We want to compare our observations to the predictions of the theory for those observations. But in the future, right, we may be in contact with other observers, and then the question becomes more interesting. Thanks.
Thank you. And then the last lightning question is really going to be lightning. The question that different people seem to have a different opinion on, so I'd like just to get yours, is can an observer arise in thermal equilibrium? Does thermal equilibrium permit observers? And there's three acceptable answers: yes, no, or it's complicated. So I'll just take a survey.
Yes.
No.
Classically, no. Quantum mechanically, question mark.
I'd be more interested in the question of how long can that observer subsist?
It's complicated.
Big fluctuations, yes.
Okay, thank you. So the next, just slightly opening it up, we seem to have in the talks and on this panel different definitions of observers, I think suited to the domains in which people are working, and different. The cosmologists seem to be talking about observers because they have to, because they want to ask questions about what observer sees, and those are necessarily indexical questions that just require you to think about observers if you are asking multiverse-style questions. The information theorists seem to be talking about observers because they want to. These systems are perfectly well defined without observers, but you are imposing on them a definition of observer to try and make rigorous what would otherwise be a fuzzy concept and seeing if you can invent a rigorous definition of what an observer is. My question is maybe for Adrian and David. Are you talking in quantum mechanics about observers because you have to or because you want to? And either of you can take that any way you like.
I think both for historical reasons and for still live intellectual reasons, it's natural to think about whether there is a fundamental role for the observer in quantum theory. But a lot of the most interesting work in the last 40 years has been pushing away from that direction. Does that answer the question?
Yeah. David, do you have anything to add?
Mostly, I think I agree with Adrian. I mean, I think that it's at least highly plausible that we have a way, outside the cosmological domain, we have a way of thinking about quantum mechanics in which we can basically get out quasi-classical emergent macrophysics, and then we can turn questions of humans and observers and the like over to other areas of non-quantum physics. And my strong suspicion is that that kind of direction works for us.
Okay, now a question for Alan and Jim. You seem to have some disagreement about questions of what Jim would call the zero-graphic distribution, including what do you do if you have two observers who see the same thing? Does that count as two observers? Does that count as one observers? As I understand it, Jim's answer is one, and Alan's answer is two. That would be your position?
Your question had a 2 in it.
What? Jim?
If you have two otherwise indistinguishable observers, physical systems that are doing the same process, does that count as two observers or does that count as one? Your zero-graphic distribution is addressing that question, right?
Yes, because it's trying to address the question of whether the probabilities that we're replicated, just exactly what Alan was saying. There are an infinite number of copies of this in the universe, so I would count that as an infinite number. I would count that as an infinite number of copies. I didn't order these theories, by the way.
It seems that you, I guess, have an example of this would be your disagreement about Boltzmann brains, where the response to theories that have Boltzmann brains is that Jim wants to change his philosophy and Alan wants to change his physics. Alan wants to throw away those theories that give you an overwhelming number of Boltzmann brains, and Jim just wants to change your philosophy that says those don't count. Would that be a fair characterization?
Well, I wouldn't call it changing my philosophy, right? Apparently, how else are we going to do the calculation of predicting what we see if we're duplicated, except by making an assumption somewhere along the line of how we're related to all those copies? So, for example, the universe is small enough; you don't need any such assumption. But here it seems we do. So I don't think that's philosophy. That's just physics. It's a question of what the model of the observer is. Did I answer the question or not?
Alan, do you want to respond to that? The purpose of these questions is to try and get you to...
Oh, I know. Wait a minute. So I don't object to people that want to reject theories with Boltzmann brains, but I don't think it's necessary. If you have a different theory that is structured with a different distribution, it isn't necessary.
Yeah, I guess maybe what I would like to ask Jim is, suppose we think about my coin flipping experiment. Suppose I flip a coin, which I'm wondering whether it's a fair coin or not. I have a theory that it's a fair coin, but I want to test that theory. Suppose I flip it 100 times and it comes up entirely heads. Is it conceivable to you that I could publish a paper saying, yeah, I think it is a fair coin, I'm just atypical?
Yeah.
If you were a referee, you'd accept that paper?
Well, we could be, but
Yeah.
I don't think that's a productive way of looking at it.
What is not a when you said that is not a productive way, which is not a productive way? Saying that we're atypical.
Sorry.
When you said it's not a productive way to look at it, I'm not sure what the "it" in that sentence referred to. Is it unproductive to say that we're atypical, or is it unproductive to? Which part of what I said is unproductive?
We have to have some typicality assumption. I think we agree on that, right? The typicality assumption can be varied to give different theories. right? And then we test the theories as usual.
Well, okay. I mean, where we disagree, I think,
So we
is
compete, assuming we're typical, atypical.
I think maybe I'll agree with you that we need to have some kind of typicality assumption, but I would say that every single paper in physics that does probabilistic calculations is making the same typicality assumption, namely that we're typical. And to assume that we're atypical, as far as I can tell, is just throwing out probability theory altogether.
It's a question of the class that we're typical of.
Explain that more clearly.
Well, for example, we have some data that were 13.7 gigayears from the Big Bang, right? We can restrict, I think, the class in which we're typical to things which have that data.
Well, okay, but then there are billions of those up there who have that data.
There are a lot
the
of
data may be
people-
incorrect for them.
Right, so I'm accepting that. I don't know whether that's
Well,
true.
then those theories would be ruled out.
Right, but so you have a different typicality assumption.
Well,
Namely, we're typical of all the instances of this particular set of data.
yeah, I agree, but I think we're always typical.
So
of,
your point is, up to now in physics, we've always assumed that.
Yeah, so I would say that everything that uses probability theory is based on the assumption that we're typical. And nowhere have I ever read a paper in any physics journal that says that my theory leads to the prediction that we should see this, but we see that, and the probability of seeing that is only 10 to the minus 30. But I think it's okay, my theory is still good, but we're atypical. I've never seen that.
Okay.
David, do you have a comment?
Yeah, I mean, just thinking about the nature of this zero-graphic distribution. So the way I naturally would think about this is somehow there's some logical grounds about typicality or similar. Let us work out what that is. But some of the way it gets discussed in some bits of the literature, and to some extent by Jim, suggests it's more that the zero-graphic distribution is part of the theory, so I can have somehow different empirically distinguishable theories with the same quantum theory but different distributions. And then firstly, I kind of don't know how I'm supposed to think about that. What's that distribution supposed to be if it's not physics but it's objective and can be found empirically? And then secondly, and I guess this is perhaps just a rephrasing of Alan's worry, I'm just concerned that I've got underdetermination. I can, for more or less any choice I make of how the physics determines the third-party probabilities, I can kind of compensate for that by tweaking the zero-graphic distribution. So I sort of worry that actually testing empirically is not going to be as straightforward there. Imagine I'm measuring some half-life of some particle or something. I'm going to be able to tweak my zero-graphic distribution along similar lines to the coin toss so as to make any... for any choice of the half-life, there'll be a choice of the zero-graphic distribution such that my data supports that choice.
You mean you have too much freedom? You can either choose a theory, change the theory, or change the zero-graphic distribution, change the philosophy if you like, and that it's not clear which you should change.
Yeah, and I guess I'm not even sure if it counts as changing the philosophy, or again, goes back to the first worry about quite how I'm supposed to understand this thing if it's not something I can work out by a priori considerations of probability theory.
And so I guess this is a question for any of the panelists who want to chime in. How do we resolve this? Is this the kind of thing where we just think hard and then realize that one position is incoherent, or are they just two physically inequivalent theories that we distinguish by observation, or are they, is it hopeless? Is it just going to be, for the next 50 FQXi meetings, Alan and Jim and others disagreeing about this? Is this right? Maybe even if a non-partisan wanted to weigh in, that would be particularly...
I think of them as different theories, and we check them by observations. So I think Alan implicitly has some kind of thing like that in ruling out theories that have any large number of Boltzmann brains. We check that by our observations.
Just a quick philosophy of science comment on that resolution. I mean, as a rule, the reason we don't tend to have haven't tended to have really long-running methodological arguments in physics is sooner or later some genuine novel prediction or set of novel predictions come up. So if you, however suspect your methodology looks like, if on the basis of your methodology you predict a certain class of phenomena that nobody otherwise expected to find, and then you go and you look at them, and in particular if your theory's made quantitative predictions that that then get borne out, then we can more or less infer from that there was your methodology was onto something. I mean, yes, something like the predictions in QED. I mean, however bothered we might have been about handling infinities of renormalization, the fact that these things were delivering such good answers told us that the methodology was okay somewhere, and if we didn't understand it, we just need to think harder about it. What's awkward, I guess, as an outsider, I don't know how or if this is going to get resolved anytime soon. What's awkward about these questions in cosmology is right at the minute they're not at stage of producing those kind of novel predictions that really clarify that. The optimist in me thinks that what we do is different people with different takes on how to do the epistemology and the methodology here pursue their research programs, and then sooner or later we get the sort of real sort of success that engages really productively with the data in a novel way. But I mean, cosmologists here can tell me if that's overly optimistic.
Right. Let's move to questions from the floor at this stage. So, David, do you want to ask the first question?
All right. So I'm going to assume you would take it as a given that your first-person probabilities would predict what the correct zero-graphic distribution is. Is that a correct assumption?
The first-person probabilities involve the zero-graphic distributions.
Sorry, the third-person probabilities.
Right. Well,
the third-person probabilities would predict...
No zero-graphic distribution there.
Yeah, but it would predict what the relevant zero-graphic distribution would be for a given set of observers.
I don't know. How is it going to do that?
So it really is an extra input?
I think so. But it's a standard input. For example, in the measure theory, right, this is also assumed.
Well, let me phrase this another way. So if you have, just staying away from infinite universes for a minute, if you have a finite universe, dynamics, an initial condition, and a suitable definition of observer, presumably the third-person probabilities would then be able to tell you what a typical distribution of observers 13.6 years after the initial condition would be. And that would be your zero-graphic distribution. Is that not a correct statement?
Let's take the Boltzmann brains again, right? I mean, it would predict, right, that there are a lot of Boltzmann brains, right? So now what?
Okay, so well,
this is going
to take me to my second question, which is, if you're taking for granted that all our predictions are indeed first-person predictions conditioned on some kind of zero-graphic distribution or initial data, to what extent is such a prediction a test of the theory itself, the boundary conditions of the dynamics, which is what we're usually interested in, and to what extent is it a test of the chosen zero-graphic distribution, which I think is part of the point that some other people are making, and how could you tell the difference? I think Alan wants to use that as a criterion, the additional input that we want to believe that we would be typical as a way of selecting among zero-graphic distributions, if not the theory itself.
I agree with you here, right? It's the combination of state, Hamiltonian, if you like, the zero-graphic distribution is tested.
Can you conceive of a way of disentangling those three things?
Well, not me yet.
Okay, we have a...
You should ask Andy Albrecht, right, who does think you can disentangle them.
Ken.
I'd like to argue that we don't need an extra assumption about typicality. Because what this assumption is supposed to answer for us is, among all of these observers who have the same exact subjective experience that I have, which one am I? But I don't think I am one of those people. I don't think it means anything to say, I'm this copy of me, I'm that copy of me. Those people are indistinguishable, and I think I'm all of them. I think if we follow the consequences of this, we will come to the conclusion, which Nick Bostrom wrote, that we should behave as if we were randomly chosen among those people, not because there is some random thing, not because there is some typicality procedure, but because that's what we should do. And then we'll get Alan's conclusions exactly.
Thank you. Next question.
As a representative of the Boltzmann brain community, I'm seriously disturbed by the prejudices I've been experiencing. Nonetheless, I'm going to ask a question formulated in my brain, which refers to the Everettian position in which being a life form, a non-Boltzmann life form, is enough requirement to be an observer. The apparatus can be an observer, a subsystem or an electron. So I was kind of touched by what Dr. Still was talking about, which was denying the status of observer to non-living systems. which I don't think would be compatible with the Everettian position, but I was thinking in particular of her requirement that it be learning, and the thought that came to mind was a volcano, which is a system which takes the path of least resistance when it has to explode, which arguably is learning to me. So I would ask her to expound a little bit more about why she's making such a demarcation.
It's funny, the chair of the physics department in Honolulu asked me exactly the same question a couple of years ago. Okay, so...
Can I get tenure?
Yeah. First of all, I don't want to be misunderstood. Like, I'm not saying that non-living systems can't be observers. That's not what I said. I said the converse, right? I said all things that I happen to care about, these living things, they are observers. So I guess I have to worry about what is an observer, you know? And then this distinction about learning and non-learning things, and why is a volcano not learning and so on? I mean, like, you'd have to be able to redo. So why would you say the volcano is learning?
Because it needs to expand upwards, and some fissures are going to be more amenable to the pressure than others. And so if its goal is to release that pressure, as it were, without being teleological, it's going to find the path of least resistance by testing.
But is finding the path of least by testing? So by trying a little bit here, trying a little bit there, and for you that's learning?
Yes.
So you think the volcano is making experiments and probing and getting data from its environment and changing its own state in response, and therefore it's learning?
Yes.
Okay.
Thanks, Susanne. And now I think David's also got a comment on this question.
I mean, just briefly, using this question of what learning is as an illustration of my definition nervousness. I mean, we have a whole bunch of things that we're confident learn, and we've got a whole bunch of things that we're confident don't. And it might be that the notion of learning has some nice clean definition that captures them, and it might be that it doesn't actually. It just it's an amorphous concept that fits a whole bunch of things. And that's largely not a useful question unless it's part of some concrete theory of learning you're building. If you're building that theory, then in that theory, learning is going to presumably be defined or defined in context, and then that theory is good for whatever that theory is good for. If it turns out that theory is really good at predicting the particular phenomenon you're interested in, and it also includes volcanoes, great. In that technical sense of learning, volcanoes can learn. If it turns out not to apply to volcanoes, too bad, volcanoes don't learn. In that kind of context, as part of some developed theory of it, it's useful to think about what the definition of learning is, but I'm not so sure it's a useful thing to exhaust ink and energy over, absent it being part of something you're going to do with that sharper definition. Ordinary language words just don't necessarily have to have super sharp crystalline definitions in that way.
Thank you. I'm going to ponder this in Poincare recurrence time now. Thank you.
And David, do you have something to say on this? Or?
Learning? Way back when I was a pup, one of the first things I did coming out of grad school, just after, actually originally Jim and I were exploring, working with him, was machine learning. And in machine learning, and also optimization theory, there are a set of theorems called the no-free lunch theorems, which are purely Bayesian and which establish, among other things, that you cannot actually prove from first principles that any one learning algorithm is superior to any other. You have to make assumptions going in. It's very intriguing to me to consider thermodynamically based quantifications of things that have parallels with learning, but as far as actually statistics in the real world, big data as it's now called, all that kind of stuff, nope, no can do, not without assumptions going in.
Thank you.
So the first thing I was advised to warn everyone in the room here that if we were going to define observers away, depending on whether they're learning or not, then those of us who have stopped learning should worry about being no longer classified as alive. My real question, pay attention, that's right, otherwise.
My real question is, I don't have a strong opinion on this, but I want to try out a defense of Jim's position. So this is kind of for Alan and David. I think the worries are well taken. It's true that if you have a kind of infinite freedom in choosing the zero-graphic distribution, then this allows basically what we would consider to be very wrong theories to agree with almost any observation. But although Jim's zero-graphic distribution may be non-typical, it's very simple to describe, right? It's just we're in this section before, shortly after the Big Bang. And so I want to draw an analogy with the past hypothesis. You can explain any observation as arising from a very non-typical state in the statistical mechanical sense of typical. The path hypothesis of statistical mechanics is very atypical, but we can state it very compactly, that it's some low entropy state with a small number of bits to describe, and it helps to explain a lot of things. And so is that kind of a defense, does that work against for Jim?
Okay. And probably Andy's question is going to be along similar lines, so maybe we should hear that first and then get responses to both.
Well, I was going to offer a point of view that a few people here already are familiar with, but I've observed that in our everyday life, the origin of randomness in our world, I've argued, is entirely coming from quantum uncertainty. And I argue that that should be the source of randomness in all our theories. That's a belief, that's a prejudice. And when I approach the multiverse with that point of view, I'm not ready to embrace a zero-graphic distribution, because that's specifically probabilities, classical probabilities inserted in situations where you don't have quantum answers to questions that you care about. Although it's very interesting to me that if I force myself to nonetheless analyze a multiverse theory and to care about these questions, the formal process causes me to introduce priors, basically, from Bayes' theorem, exactly in the same form as the zero-graphic distribution. So mathematically, we're exactly on the same page. It's just I believe you have to, then we get to Alan's comment where people don't publish papers where they say, here's my result, but I've chosen this way out to lunch prior, so I interpret it differently, although they do that in the middle of the distribution, right? You can have one prior or another. So that's the interpretation. Then in terms of the measures that Alan was talking about, I think it's an open question how much of that may eventually come from a systematic, so maybe some of those measures are actually going to come from quantum mechanics when we understand the theory better. And that's actually why I'm feeling more open about maybe the multiverse is going to work out. That maybe some of these measures can be made more rigorous ultimately, or maybe not. So I don't know to what degree those measures are, priors that I'll never really like, or never really want to be part of the predictive power of the theory, or within the quantum uncertainty.
Quick comment about your question. Should two instantiations of the same observer should count as one or two? And in a sense, all we know for sure is that all of us are like roughly 10,000 seconds long stream of consciousness that think they're spending a day at an FQXi conference. So could we be at the same time Boltzmann brains, evolved animals living 13.8 billion years after the Big Bang, bored superhumans, just we've rendered ourselves amnesiac to have fun, and maybe it's no problem in the same way that when I'm driving on a highway that has two road numbers, it's pointless to argue, am I on this road number or this road number? And in an infinite universe, there's no measure. So it's a worrisome thought, but it's something that I keep thinking about. So.
Okay, do we have any responses to any of those three questions from the panel? Alan.
I would like to respond to the analogy about the past hypothesis. In the past hypothesis, what we're saying is that what we think is the most likely trajectory that got us here is not one that's typical in the ensemble of all trajectories, but there's no particular reason to think that the ensemble of all trajectories has anything to do with anything, as far as I can tell. So we adopt the past hypothesis, I would say based on Occam's razor, that it gives us a simple theory that's predictive, and we test that theory all the time, and it seems to work. In the case of the multiverse, however, the infinite number of copies of beings that think that they're Alan Guth are all absolutely identical. And we literally have no way of distinguishing which of those that we are. Ken Olam suggested that we really are all of them. That's even meaningless to ask which one we are. And under those circumstances, it seems to me that the only reasonable hypothesis is that we're equally likely to be any one of them, and that no other hypothesis really makes any sense at all.
Yeah, I mean, this is, I guess, picking up a little indirectly on some of what's said. This is just an observation about the severity of the Boltzmann brain problem. And I think it's very tempting, and certainly from a sort of philosophy point of view, very tempting to say, well, okay, when you've got just thoroughly deluded agents, you can say, well, those shouldn't count in some sense. We should just as methodologically say that's a skeptical hypothesis, I suppose, one of those, put them away. But fine, let's have fluctuations in the vacuum, assuming there are such fluctuations, assuming the physics works the way it's being claimed to work. Let's have fluctuations that are 10 billion light years across. If you're living in one of these fluctuations, all your zoology is fine, all your history is fine, and by all means confine your attention to people who've still got 1 billion years of the fluctuation to run. All your mundane predictions about presidential elections and the fate of your own star and stuff, and how you'll travel across the world, all that stuff is fine. The only things you're deluded about in this situation are some relatively specialized facts about cosmology, which, with all respect to what we do in our lives, don't seem to be the main part of the epistemology of most observers in these bubbles. And there are many, many fewer, in some appropriate sense, of these fluctuations than there are brain size fluctuations. But there are still, as I understand it, infinitely more of these 10 billion light year wide fluctuations than there are us in the original bit of the universe. So I think the demands required on a kind of exclude these things on general methodological grounds are more severe than they look if we're literally thinking about just Boltzmann brains. Boltzmann gigaparsec wide regions will do the work just as well.
Everybody thank the panelists.